Section 4.4 is on probability multiplication rules. We're going to cover statistical independence, conditional probability, which is definitely a little tricky, multiplication rule for dependent events. So we're going to go through some symbols that you might see in the unit. Some of them we've covered in previous lectures, but we're going to codify it and put it all together here with the different symbols that you could see and what they really mean. So you might see A meaning event A with an exponent C meaning its complement. So that includes everything not in A or 1 minus everything in A. A intersect B. That upside down U means that it includes only things where they happen in both A and B at the same time, as opposed to A union B. A union B, or an or statement, A or B, includes if it happens in just A, happens in just B, or if it happens in both groups. The new thing that we're going to be focused on this lesson is this way of saying a conditional statement. The way that I read this statement is the probability that A occurs given that event B has already occurred. So this line I call the given line. The thing after the given line we assume has already happened. So we're asking what's the probability event A happens if we know event B has already happened. This means A given B, it's the probability event A happens if you already know event B has happened. This is just showing that we can put two concepts together. Specifically, here we're putting the concept of an intersection with the concept of a complement. If we include everything that's in A and B and then take its complement, that means that we're taking the intersection of A and B, figuring out what belongs to that set, and then saying, no, we want everybody else. So if I wanted the complement of females wearing glasses, I'd figure out who fits both groups, females and wearing glasses, and then do 1 minus that out of the number of people in the group. So if 5 of the 25 students in my class are females wearing glasses, the complement of that is 20 out of the 25 students in my class, which represents the people who are not females wearing glasses. It would include females not wearing glasses, it would include males wearing glasses. So again, really this is just showing how I could put two such concepts together. I can have an intersect where I then take the complement of that intersect. Similarly, I could condition or put a given line around an intersection or union. It's not something that we're going to cover in this class. Really, this is about as hard as we'll get as far as putting multiple concepts together, but do be aware that all of these concepts I can combine in one way or another. The multiplication rule for independent events is the way we'd like it to work. Basically, if we take the probability of one thing occurring times the probability of the other occurring, that's the way that the multiplication rule works if we know things are independent. Unfortunately, that's a big if. Normally, we do not know that events are statistically independent, and we're going to get into more detail on what that really means later in this lecture. But for now, what you need to know is if we do have independent events, and we want to find the probability of both occurring at the same time, we take the probability of the first event times the probability of the second event. So let's say I'm going to flip a coin, roll a die. The coin does not affect what happens on the die and vice versa. That's why really they're statistically independent. Knowing what happens on one doesn't impact what I think happened on the other. That said, if it's 50-50 whether I roll a heads or tails, and if it's 1 out of 6 or 0.17 that I can roll exactly a 3, then probability of rolling a heads and getting a 3 would be 0.5, the probability of getting a heads, times 0.17, the probability of rolling a 3. So really about 8.5% of the time, if I roll a die and flip a coin, I'll get heads on the coin and 3 on the die. 25% of Manor students are nursing students. These numbers are made up, by the way, so they're not accurate. I don't know what the real number is. 60% of Manor students are female. If these two events are independent, what's the probability a randomly selected Manor student is female in the nursing program? If they're independent, we would take 25 or 0.25 times 60% or 0.6. 0.25 times 0.6 would give me an answer of 0.15. So 15% of students randomly selected in the Manor population would be a female in the nursing program if these two numbers were correct and if they were statistically independent. But what would that really mean to say that they're statistically independent? It would mean the fact that knowing one of the two things was true would not impact whether I thought the other thing was true. So if you told me a student was female, that would have no impact on whether I thought they were a nursing student or not. If you told me that student was a nursing student, that would have no impact on whether I thought they were female or not. In reality, that's probably not true. Knowing one probably impacts the other because it's very unlikely that a specific program has the exact same breakdowns as the college as a whole. So it might be that there's more females in the nursing program than the college in general. It might be that there's less. Regardless of which way it is, knowing that they're in the nursing program is going to change my opinion of whether I believe them to be female or not, assuming that they're not the exact same percentages, female within the nursing program and female within the college in general. So if we knew that 80% of nursing students were female, once you told me someone was a nursing student, it would increase whether I think they were female. For that reason, they would not be statistically independent events. This leads us into the idea of conditional probability, because we're going to need to use conditional probabilities to find a multiplication rule that does work when two events aren't statistically independent. So where we're going to begin is with the idea of conditional probability. We have here two events, E and F. The way this is written is the probability that event F occurs if we already know or given that event E has already occurred. The way that you find this probability is you make it only out of the times that E has occurred. Since we know E already happened, we don't have to take the whole sample space and find the probability out of the whole sample space. We're limiting the sample space to knowing already E has occurred. So the only possible outcomes that could have occurred are ones that are included in E. We can eliminate everything else that was in the sample space because we know E happened. So if it's not part of event E, it doesn't matter to our calculation at this point. That said, the top does contain things less than just what's in E. It only contains things that are in both E and F. So if we take the things that are in both E and F divided by only the things that are in E, that's going to give us the probability that F occurs if we know E already occurred. If we know E already occurred, then for F to occur, both E and F have to occur. So, the conditional probability that I'll roll a number less than 4, given that I rolled an even number, would be calculated as probability less than 4 given even equals the probability of both things occurring divided by the probability of even. So the probability of even and less than 4 is only one possibility on the dice, a 2, which is both even and less than 4. That's where this 1 out of 6 comes from. The probability of getting an even number is 3 out of 6, rolling the 2, 4, or 6 on the die. That's where this 3 out of 6 comes from. Really, if you wanted to see the fraction math that goes on here, dividing a fraction by a fraction means I flip the second one and multiply. So I'm multiplying 1 over 6 by 6 over 3. The 6's cancel and leave me with 1 over 3. So if I know I got an even number, the probability that it's less than 4 by the formula is 1 out of 3. If we think intuitively about what's happening here, if I rolled an even number, I rolled a 2, 4, or 6, the one of those that's less than 4 is the 2. So of the 3 possible things I rolled, one of them is less than 4. That's why the probability I got something less than 4 given I got an even is 1 out of 3. You have two dependent events, A and B. Let's define the events. A, you had class on campus today. B, you ate lunch on campus today. We know the probability of A equals 0.8. 80% of the days you have class on campus. We know the probability of B equals 0.3. 30% of the days you eat lunch on campus. If we know P of B given A equals 0.25, how do we solve for the probability that both occur? Basically what we've done here is we found a way to work backwards to get to the multiplication rule for dependent events. If I look up at my formula here, we're really solving for this top part, P of A and B. As far as what they gave us, we don't really need this P of B. everything else is useful, but really that's not going to be part of the equation because we're not conditioned on B after the given line, we're conditioned on A. So to figure out and solve back for this P of A and B, what we're going to do is put P of B given A here as 0.25, put P of A here as 0.8. If we multiply both sides by P of A or 0.8, we'll get an answer here that's exactly equal to P of A and B. So really we're using algebra to rearrange the formula to find the probability of P of A and B using dependent events instead of independent events. So here's what that looks like. We put in 0.25 here, we put in 0.8 here, I multiply this side by 0.8 to get rid of the 0.8s, I multiply 0.25 by 0.8, and that's how I get 0.2. 0.25 times 0.8 equals P of A and B, which is 0.2. So using the probability of A, the conditional probability of B given A, we were able to solve the probability of A and B together. Really, I can put that into a single formula that's just a rearranged version of that previous formula that tells me if we have dependent events, the probability of both of them occurring together, P of E and F, can either be written as P of E times P of F given E, or P of F times P of E given F. Both of these are mathematically equivalent. Basically, the first one says, if we know E already occurred, that's where the P of E is coming from. Multiply that P of E times the conditional probability that F occurs if we already know E happened. Or we can condition it on already knowing F happened. If we already know F happened, then we take the probability that F happened in the first place times the probability that E happened, given that we know F already happened. So this shows how we would find the probability of rolling an even number and a number less than 4 at the same time. We know the even numbers less than 4 is only 2. 2 is one of the possible 6 values on the die, so we should get 1 out of 6 or 0.17. This formula gets us there by taking P of even, which is 0.5, times P of less than 4 given even, which we found on a previous slide to be 1 out of 3 or 0.33. When we multiply them, we do get 0.17 or 1 out of 6. If we didn't use the conditional probability formula for this, and we just multiplied the 2, it would be 0.5 times 0.5, which would give me 0.25, and would be an incorrect answer. It would not match with the reality of what's going on. The reason it wouldn't match is because knowing whether it's even gives me information about whether I think it's less than 4. Since it gives me information and changes my opinion, it's a dependent situation where I can't use that original rule and just multiply the two events. In two-way tables, when we talk about how we use conditional probability, basically what it does is it isolates a row or a column. So before, whenever we were looking at two-way tables like this and trying to figure out probabilities, we went to the table total for the bottom of our fractions. Now when we do conditional probabilities, the bottom of our fraction is either going to be a row total or a column total. For instance, in this first question, what's the probability I got a pretzel given that I made the purchase on day 1? Well, if I know I made the purchase on day 1, this is the only row of the table that matters. I don't care anymore about day 2 or the totals. All I care about is what's happening in day 1. So in day 1, there were 95 total items sold. That's going to be my denominator. Of those 95 items, the ones that were pretzels is 55. So if given day 1, we want to find what's the probability it was a pretzel, 55 of the 95 items sold on day 1 were pretzels. If we condition it the other way and say we know we sold a pretzel, what's the probability we sold it on day 1? Well, in that case, after the given line is pretzel, meaning we're isolating a column, not a row. We don't care about the water bottles, we don't care about the total. All we care about is the pretzels. Within the pretzel column, we have 93 possibilities. Of them, 55 were on day 1. So to find this probability, the probability it was on day 1 given it was a pretzel, of the 93, 55 were on day 1, so it would be 55 divided by 93. When we do water bottle given day 2 means we isolate this row. Out of the 65 purchases on day 2, 27 were water bottles. So the answer to this question would be 27 divided by 65. Finally, day 2 given water bottle. If we know it was a water bottle, we know it was from this column. 67 total water bottles were sold. Of them, 27 were sold on day 2. So this answer would be 27 divided by 67. If we look at it now from one of the decimal versions, here if we're trying to find the probability that they're from New York, given that they spend more than $50, we'd start by saying after the given line is spend more than 50. So spend more than 50 is this row. This row total was 0.14 plus 0.42 is 0.56. Out of that total 0.56, 0.42 were from New York. So I do 0.42 divided by 0.56 to find this conditional probability. When we look at the second one, it's conditioned on being from Philadelphia. From Philadelphia is this column with a total of 0.24 plus 0.14 is 0.38. Out of that 0.38 that came from Philadelphia, the ones that fit spending $50 or less, is this 0.24. So 0.24 divided by 0.38 would give me the answer to this bottom question. Notice that this goes to the next step of actually putting it into the calculator and getting an answer. 0.42 divided by 0.56 gives me an answer of 0.75, and 0.24 divided by 0.38 gives me an answer of 0.63. Again, before I got these answers, I really want to have my totals for each of the rows, each of the columns, so that I could see where this is coming from, where basically this 0.14 plus 0.42 is just this row total. This is saying take the row total for spend more than 50 and put what's from New York on top of it. Finding which events fit and their probability. So this is going to be a series of slides using the same information, which there's questions in Cengage that are somewhat similar to it. Basically, in this situation, we're given 10 equally likely events. We number them event 1, event 2, event 3, event 4, event 5, event 6, event 7, event 8, event 9, event 10. If we wanted to write out the full sample space, we'd write a brace, E1, E2, E3 up to E10. We then define specific events. Event A is E1, E2, E3, E4, and E5. Since there's 10 events all equally likely, each one has 0.1 probability of occurring. 1 divided by 10 is 0.1. So if in event A we have 1, 2, 3, 4, 5 things with 0.1 probability each, that means there's 5 times 0.1 or 0.5 probability we belong to this group A. Group B is E3, E6, and E9. 3 possible events, each worth 0.1. 3 times 0.1 means the total probability is 0.3 of event B. Event C has E2, E4, E6, E8, and E10. 5 events out of the 10 total. That's why it occurs with probability 0.5. In the slide to come, we're going to see how to calculate the probability of A complement from this information, the probability of A intersect B, A union B, and A given B. When we start with the probability of A complement, really the formula for a complement is just 1 minus that original probability. So the probability of A complement is 1 minus the probability of A. We were given that the probability of A is 0.5. If I do 1 minus 0.5, I get 0.5. If I wanted to write out the events that count, since event A is event 1, 2, 3, 4, and 5, its complement is everything else in the sample space that's not included. Specifically events 6, 7, 8, 9, and 10. There will be questions where it asks you to list what events are included before it asks you to calculate the probability. When we're asked what is the probability that we get A and B at the same time, we look at the 2 lists and we say what is occurring on both lists. E1's on A but it's not on B. E2's on A but it's not on B. E3 is in both A and B. So that's one event that counts as being in both lists. E4 is in A but not B. E5 is in A but not B. E6 is in B but not A. E9 is in B but not A. So the only event that overlaps is this event E3. For that reason, one of the 10 is in both A and B, so the intersection A intersect B includes only the event E3, which means it occurs with probability 0.1. 1 of the 10 events counts. 1 divided by 10 would give me 0.1. If we instead talk about the union includes everything in A and everything in B, not counting their overlap twice. So I start by listing E1, 2, 3, 4, and 5. E1, 2, 3, 4, and 5 all count because they're all in A. When I get to event B and I start listing those things, E3 would be the first thing that counts, but I've already listed it here. So I don't list something twice, I move on to the next event. Event 6 wasn't listed in A, so I'm going to list it in the OR statement or the union. Event 9 also wasn't listed, so I'm going to list it here. That means I have 1, 2, 3, 4, 5, 6, 7 total events that fit A or B. 7 of the 10 gives me 7 divided by 10, or 0.7 as the probability of the union. If I want to find the probability of A given B, this is the first time where we're not going to have the denominator of our fraction be 10. What we're really going to do is only look as a sample space at the things that came after the given line. So in this case, after the given line is B, meaning we know event B already occurred. If event B already occurred, the only possibilities are we got E3, E6, or E9. So the divisor in our fraction, or the bottom of our fraction, is going to be 3 for the 3 possible events that occurred. The top of our fraction is which ones count as happening in both A and B. So the general formula is A intersect B over P of B. In this case, the only thing that's happening in both A and B is still E3, so 1 of the 3 events in B count as happening in A. Since 1 of the 3 events, E3, out of E3, E6, E9, it makes the probability 1 divided by 3, or 0.33. So we're using the formula, we're also using our ability to look at what is in the sample space versus what counts as being in both sets. So here, sample space is limited since it's after the given line B to these 3 events, 1 of which is also in A. That's how I get 1, the events that I'm allowed to use from B that are also in A, divided by the total number of events in B, because it's what came after the given line. 2 events are mutually exclusive if they cannot happen at the same time. Students get confused on the difference between mutually exclusive and complements. 2 things can be complements and mutually exclusive. In fact, for something to be a complement, it must be mutually exclusive to the original event because they can occur at the same time. But I can have mutually exclusive events that don't represent complements. For instance, if I roll a die and get a 3 versus if I roll a die and get a 6. Those are mutually exclusive events, but they don't represent complements of each other. The complement of 3 is everything but 3, so rolling a 1, 2, 4, 5, or 6. The complement of 6 is everything but 6, so rolling a 1, 2, 3, or 5. That's not what's happening here. What's happening here is I have 2 individual rolls. If I put them together, I'd only have 2 of the 6 possibilities. I wouldn't have the whole sample space. But they still represent a mutually exclusive situation because they can't happen at once. I can't roll a die and get both a 3 and 6 at the same time. I either got a 3 or I got a 6. As opposed to flipping a coin and get heads versus getting tails. These are mutually exclusive. I can't get both heads and tails at the same time, but they're also complements of each other. If I know I did not get heads, then I do know I got tails. So it can be the case that they're both mutually exclusive and complements. It's just not required that once they're mutually exclusive, you know they're complements. Here's another example where they wouldn't be complements. If I know what's going to happen in a month or whatever when we vote, maybe you're watching this far in the future and it's not in a month, but when the voting occurs, citizens can do one of 4 things. They can vote for Joe Biden as President of the United States. They can vote for Donald Trump as President of the United States. They can vote for another candidate running as President of the United States, or they can choose not to vote in the 2020 election. This represents everything that could happen. If Somebody tells me they voted for Biden, I know for a fact they didn't vote for Trump. They are mutually exclusive events. I also know for a fact that they did vote. So if you tell me you voted for Biden, you can't belong to the group that did not vote. Those are two different things that are both mutually exclusive to voting for Joe Biden in the election. So again, mutually exclusive events don't occur at the same time. What that leads us to is a slightly changed addition rule. Before we had to add each of the probabilities and subtract out their overlap. When we have mutually exclusive events, there is no overlap. They can't happen at the same time, so I don't really need that part of the formula. If I'm told up front the events are mutually exclusive, then to find the probability of them both happening, then to find the probability of either of the two happening, I can just add the two individual probabilities. So if, for instance, I'm told the probability of A is 0.35, probability of B is 0.50, and I know they're mutually exclusive. First things first, the probability they occur together, 0. It's 0 because they can occur together by the definition of mutually exclusive. No chance that both A and B are happening at the same time is the whole idea of mutual exclusivity. So here this is probability 0. A union B, one or the other, I can just add the two probabilities without having to subtract anything. So 0.35 plus 0.50 would give me 0.85. For the probability of A given B, this would really be the probability that both happen at the same time divided by the probability that B happened. But we know there's 0% chance that both happen at the same time, so this ends up being 0. Another way of seeing it is, since it's conditioned on B already happening and we know they're mutually exclusive, if B already happened, we know there's a 0% chance that A is going to happen. So here are those answers, 0, 0.85, and 0.